Today's video is analog Butterworth filter. The question may be, why analog filter? Our aim is to design digital filters or IIR digital filters. But before we design IIR digital filters, we will design analog filters in S domain. Then we have different transformation techniques. By using those transformation techniques, for example, bilinear transformation method or impulse invariant transformation method, we can transform the analog filter designed from S plane to Z plane. Now to start with, we have three widely used filters, that are Butterworth filter, Chebyshev filter and elliptic filter. Among the three, elliptic filter is the most optimum filter. That is, if the order of the filter is capital N, then we can design an elliptic filter with minimum N meeting all the specifications required for the filter. That is, the minimum N, minimum order of the filter can meet us the required specification in case of an elliptic filter. But the computational process or the mathematics is bit complex for elliptic filters, so engineers do avoid the elliptic filters and go for Butterworth or Chebyshev filters mostly. Among Butterworth and Chebyshev, Butterworth is the most simple or simplest compared to Chebyshev filter. But the cost may be higher compared to Chebyshev. Now, we start with all pole low pass filter. We know from low pass filter we can shift to other forms of filters, that is high pass and band pass or band stop. So studying low pass filter is sufficient enough. And here we study all pole low pass filters. That means the magnitude of the filter will have only poles. But we know the number of poles should be equal to the number of zeros. That means there are zeros. There are zeros as much as there are poles, but the zeros are in infinity. So, for example, HAS, that is the magnitude of the filter in S domain, would be some constant divided by S to the power n plus a n minus 1, that is having n number of poles. So here, whenever we are to design an analog filter, we are to find out HA of S in terms of some constant divided by the denominator, which will be in terms of S. What we will be specified by the as per the requirement or in the problem given to us is del P, del S, omega P and omega S. This capital omega is used for our analog domain, while in digital domain we use small omega for angular frequency. Now we will be given del P, which is the magnitude of pass band, del S, which is the magnitude of stop band, and omega P and omega S are two frequencies of pass band and stop band respectively. We are to design a filter. Here we are talking of a Butterworth low pass filter which will specify this del P, del S, omega P and omega S. Now, to start with, I will always mention that whenever you are given some specification, it won't be possible to fully specify all the mentioned or given specifications. What we are to do is always keep in mind or keep a track of omega p, because omega p is the pass band, that is our concern. Omega s, we can make some adjustment with omega s. For example, if we shift omega s closer to omega p, then it is a win-win situation for us, that is better than what we were asked to do. But we should never compromise with omega p. Omega p is sacred and should be satisfied fully. Now, for a Butterworth, analog Butterworth low pass filter, the magnitude square is equal to, as per definition, is equal to 1 by 1 plus omega by omega c to the power twice n, where n is the order of the filter. Now we see at omega is equal to omega c, we find that HA squared is equal to half, irrespective of the value of n. So here omega c is called the minus 3 dB frequency of Butterworth filter, or also the cutoff frequency of Butterworth filter. Now we can see that as we go on increasing the order of n in the specified direction in the diagram, the characteristics of the ideal characteristics is shown here by the sharp lines. That is, it suddenly comes from 1 to 0. But as I told you, as discussed previously in the previous videos, sharp transition is what is not required. We need monotonic decrement. See here, as n goes on increasing, the decrement becomes more slower, or we can see that the characteristics of the filter moves more towards the ideal characteristics. So here, error, which is defined as magnitude of 1 minus magnitude of Haj omega, or we can say the difference between the curve and the ideal characteristics, is the error. So the error decreases as we go on increasing n. Now, that means we can say, in order to get a good low pass filter or a better filter, we have to go on increasing n. But there is a problem over here. Increment in n means increment in cost, and when you are, as an engineer, you are working for a company and you are going where they are making billions of filters at a time, then if you go on increasing n, it will cost you a huge amount which is not required. So optimum n is, or the base minimum n, which ensures or which satisfies the specification, is sufficient enough. We will not unnecessarily go on increasing n. So in order to design our analog low pass Butterworth filter, the two terms that we will be wanting to know is omega c and the order n. If we know these terms, we can write the equation of the Butterworth filter. Now, we see that we can write Haj omega in this. If we take it to the numerator, we can write it at whole to the power minus of half, and if we expand it, it would be 1 minus half omega by omega c to the power twice n, plus higher orders of omega by omega c to the power twice n. Now if we differentiate both the sides with respect to omega, we see that at omega is equal to 0 point, the differentiation will be equal to 0. And not only once, if we differentiate the term Haj omega with respect to omega for ith times, where I is equal to 1 to going from 1 to twice n minus 1, at omega is equal to 0 point, for every differentiation, we will see that the value becomes equal to 0. Now, from the concept of mathematics, we know that at any point, if the derivation becomes equal to 0, then we call that the function has a maxima or minima at that point, that is, the function is flat at that point. But here we see the function is flat at that point for many differentiations, for many derivatives, that is, for ith derivative. So we can say that the function is maximally flat at omega is equal to 0. Now, writing Haj omega whole square is equal to 1 by 1 plus omega by omega c to the power twice n won't be sufficient enough in order to satisfy all the specifications that would be given to us. So we need to have a different approach. We need to write Haj omega. We need to find Ha of s from Ha of j omega. So Haj omega whole square can be written as Has into Ha of minus s. And we replace omega by s by j because s is equal to j omega. So omega is replaced by s by j. So here we see we will have different poles of this function. So if half of the poles are assigned to HAS and another half is assigned to HA of minus S, we will get to know HA of S because our aim is to find HA of S. From all the poles that we will get from this function, half of the poles will go to HA of S and half of the poles will go to HA of minus S. Now, this half of the poles that we will assign to HA of S because we need a stable low pass filter. In order for the system to be stable in S plane, all the poles should lie in the left hand plane, as you know from your S domain. Knowledge of S domain. All the poles for Z transform, all the poles should lie between an unit circle. For S plane, all the poles should lie in the left hand plane. So we have to consider those poles which lie in the left hand plane. Now poles, for finding poles, we can write minus s square by omega c whole square to the power n is equal to minus 1 because the denominator should be equal to 0 for finding the poles. And minus 1 can be written as e to the power j twice k minus 1 into pi, where k goes from 1 to n. And this n, from the previous step, this n can be replaced from that power to pi by n. Now from here, what we can find out is s square is equal to minus omega c square e to the power j twice k minus 1 by into pi by n. So sk, let us name it as sk. Sk is plus minus j omega c e to the power j twice k minus 1 into pi by twice n. So here we have two set of poles. Here k goes from 1 to n. Now here we have two set of poles. One is the positive set of poles and one is the negative set of poles. We will see that the positive set of poles are the poles which lie in the left hand plane. Now how? Let us take the positive sign. Say sk is equal to plus j omega c. Now e to the power j twice k minus 1 pi by twice n can be written as cos and sine in this way. Now, if we multiply by j, what we have is omega c minus of sine twice k minus 1 pi by twice n plus j cos twice k minus 1 into pi by twice n, where k goes from 1 to n. Now, for the first term, now take the real term. The real term is the sine term. Now, if for the first term, where n is equal to 1 and k is equal to 1, what we have is pi by 2. And for the last term, what we have is 1 minus, for the last term what we will have is say k is then n, k will be n. K will be n. So anything which is less than pi. For the first term, so that means if k is 1, when k is 1 and k is n, we see all the things are less than pi. That is in the upper half of the plane, that is less than pi by 2, that is in the left hand plane. So this sk stands for sk, only the positive term we will take, positive poles we will consider. Now if we consider the positive poles, then sk by omega c would be this. Now when n is equal to 1, then we can write the pole as 1 by s plus omega c, s by omega c plus 1. Then if n is, see here, if we put n is equal to 1, what we have is k is going from 1 to n. If n is 1, then we have minus sine pi by 2 plus j cos pi by 2, because n is 1. So cos pi by 2 is 0, sin pi by 2 is 1. So S1 or S by omega c is equal to minus 1. So the pole becomes 1 by S by omega c plus 1. So if n is equal to 2, if n is equal to 2, we have n equal to 2 means we have pi by 4 minus sine pi by 4 plus j cos pi by 4. Now this becomes a complex pole, that is s by omega c is minus 1 by root 2 plus j 1 by root 2. If there is a complex pole, the other pole will have its complex conjugate. So we need not go into the next pole, which will be for k is equal to 2, because here k will go from 1 to 2, because here n is 2. So for 1, k is equal to 1, we have 1, n is fixed at 2, and then k will vary as 1 and 2. So for k is equal to 1, we have minus 1 by root 2 plus j 1 by root 2. For k is equal to 2, we will have minus 1 by root 2 minus of j 1 by root 2, which is complex conjugate of each other. That means if we find one complex pole, the next pole will be conjugate of each other. So here HAS would be 1 by S by omega c plus 1 by root 2 plus j 1 by root 2 multiplied by S by omega c plus 1 by root 2 minus j 1 by root 2. So this is the HAS if n is 2 for Butterworth filter. Similarly, we find for n is equal to 3. We see when n is equal to 3, then k would be 1, 2, 3. For the first, when k is equal to 1, we have s is s by omega. If we take as omega c as 1, then we have s is equal to minus 1, and the next two poles are complex conjugate. So if HAS, the HAS when omega c is equal to 1 can be written as this. Now here, if omega c is not 1, we can divide every s by omega c and we can write this equation. Now here we can be convinced by the three examples, n is equal to 1, n is equal to 2 and n is equal to 3, we can be convinced that if n is odd, then we always have a real pole as minus 1. See, for n is equal to 1 and n is equal to 3, in both the cases we had a real pole when s by omega c is equal to minus 1. If we take omega c 1, then s is equal to minus 1. But if n is, and all the rest poles are complex conjugate of each other. But if n is equal to even, then we do not have a real pole and all the poles are complex conjugate. So in general, we can write this equation. That is, if we multiply the two complex, if there are real poles at -1, we can multiply that term. But what about the complex pole? The complex pole in general is this equation, which comes from this first equation. We have this equation. From here we can write the complex poles. So the complex poles are this. Here 2 sine twice k minus 1 pi by twice n is written as bk. So from now onwards, we don't have to find the poles separately. Once we know our n, we can directly find the denominator of the Butterworth. And the denominator of the Butterworth filter is called the Butterworth polynomial when we take omega c is equal to 1. I'm again repeating, the denominator of the HAS, that is the denominator of HAS, is called the Butterworth polynomial when we take omega c is equal to 1. Now here, once we can chalk down s square plus bks plus 1, where bk is equal to twice sine 2k minus 1 pi by twice n, we can write the HAS for every Butterworth filter depending upon the order of the Butterworth filter, that is n, capital N. Now for n is equal to even, we know there is no real pole. So we have in the denominator s square plus bk omega cs plus omega c square, where omega c is not equal to 1, and in the power we have omega c to the power n. It is a product of this. So we can write k going from 1 to n by 2, because this poles will be multiplied together. That is s square plus b1 omega cs plus omega c square into s square plus b2 omega cs plus omega c square. In this way they will be multiplied. Here bk will keep on changing as your k changes from 1 to n by 2. And if n is odd, we know there will be a real pole at s is equal to minus omega c. That is s by omega c is equal to minus 1. So you have this extra term and the rest term, but k is, as n is odd and k goes from 1 to n, here k will go from 1 to n minus 1 by 2 terms, and the numerator will have omega c to the power n, and bk is given as. So from here we can say that in order to write the HAS of a given specified Butterworth filter, we first need to know capital N. Then take the decision whether n is even or odd, what form we have to write the polynomial, or in what form, which, if n is even we have to write the first equation, if n is odd we have to write the second equation, and then keep on changing bk and keep on multiplying those poles. And if n is even, we will have no real pole. If n is odd, there will be a real pole. So the knowledge of n and omega c is important, as I have also said previously. So here we will be depending on omega c and n. So, but the problem is we will not be specified omega c, or we will not be specified capital N. What we will be specified is del p, del s, omega p. So now here our del p is equal to 1 by root 2, and then omega p will be equal to omega s. Now If omega is omega s, then the magnitude Haj omega is del s. From the first, we know Haj omega whole square is equal to 1 by 1 plus omega by omega c whole to the power twice n. So the magnitude, if omega is omega s, then Haj omega is del s. So we replace omega by omega s and Haj omega by del s, and we get a value of n. In the second step, we can take 20 log 10 on both the sides, and we will have n is equal to this. Now, it is no guarantee that n will always be an integer. The left hand side will always yield an integer result. So what we say, for example, if you have 7.8 as the result, we have to take the next higher value, that is 8, but keep it close to what we have got, not go beyond that, then there will be increment in cost. So we put a greater than sign, that is n is greater than equal to half of what is written here. Then similarly, we can satisfy our pass band as well. That is 1 by 1 plus omega p by omega c whole to the power twice n would be equal to del p square, and 1 by 1 plus omega s by omega c to the power twice n will be equal to del s square. We are trying to satisfy all the specifications given to us. Then if we divide the two equations, what we have is omega s by omega p whole to the power twice n will be equal to del s to the power minus 2 minus 1 by del p to the power minus 2 minus 1. So from here we can again write n greater than equal to half of, taking log on both the sides, half of log 10 del s to the power minus 2 minus 1 by del p to the power minus 2 minus 1 by log 10 omega s by omega p. Here we can satisfy both del s, del p, omega s and omega p, which will be given in our problem. Now, the next term what we need to know is omega c. Now, from here we can see both the equations which satisfy the pass band and which satisfy the stop band will give us our omega c. But we will choose our equation which satisfies the pass band. As discussed previously, pass band is the sacred band. So here from this equation we can find out omega s. Again, I would like to express that del p and del s are sometimes expressed in decibels, which are represented as AP and AS. That means 20 log 10 del p will be equal to minus AP. Why minus? Because 20 log 10 1 is equal to 0. Anything below that is negative. So 20 log 10 del p is equal to minus AP, and 20 log 10 del s is equal to minus as. That means del p is equal to 10 to the power minus ap by 20, and del s is equal to 10 to the power minus as by 20. That means in the problem, whenever you will be given ap as omega p omega s, from ap as convert it into del p del s. Once you know del p del s omega p omega s, try finding out n and omega c. Once you have n and omega c, depending upon whether n is even or odd, you need to write our HAS, the form of HAS. Now, depending again on n, vary bk, k vary k, accordingly bk will vary, and write the product of the sum in product of the sum form. That will give you our HAS. This is all in today's video. In the next video, we will study about Chebyshev filter. Thank you class for now.